this is a great opportunity. And the field of deep learning-based imaging has been greatly developed over past several years. So we still do deep learning, but we see some new important trend. And in our opinion, DL means deep learning, but also means diffusion and large models. So my group has been working on diffusion models and large models, as we will report as follows. And we have grouped several postdoctoral fellows here. I use color coding, so you see their name RGB. And really, my student Chris couldn't come here for family reason, and he is a great student, NSF fellow. So his part was done in collaboration with Chuang, so the orange should be blue. So just make sure. So, okay. The diffusion model, I really like Webb's talk, and he overviewed the diffusion model very well. So I have little to add. But to me, the diffusion model is really a very good way to model data distribution. So we know in reconstruction field, we do likelihood-based reconstruction. Why? Because you do not know probability distribution of images. Now with the diffusion model, we can model the P of X. X is image. Actually, conditional model, conditional probability can also be modeled that way. Very powerful Bayesian modeling and inference tool. I like very much. Then we talk about big model and the news everywhere. So I think the most intriguing thing is emergent properties, and I list a few there. And this is something very, very important. No time to chat further. Outline. We talk about several projects. First three are adaptations or applications of diffusion model. Last one, and Chuang's main work, large hybrid model. Hybrid means image, text combined, or visual linguistic models. And so we do that part and very seriously. So first topic, diffusion model, we work in latent space. With diffusion model, we synthesize data set. In terms of statistical distribution, the same as our original one. It's a good way for federated learning, right? And also photon-counting is a great topic in the CT field. And we work with GE, and we do some super resolution denoising deep learning. So we use Bruno's group developed CT simulators, and Hongyong also key collaborator there. And the third one is also interesting. My new postdoc, Wenjun here, he will present diffusion work. But diffusion model, you know, is intrinsically is sequential processing. And his first project is to make a diffusion model parallel computing scheme. And we do patch-based or sub-volume-based diffusion. You will hear more detail. Large model really needs big data and high-performance computing resource. And it's fortunate, RPI has great computing resources. So we have good number of PC clusters. Supercluster has about actually over 1,000 GPUs, and we only have 2 of them. Okay, so we move to the first part. So Yongyi, please.
Hello everyone, my name is Yongyi Shi. I'm pleased to have this opportunity to share my recent work here. In this work, we used the latent diffusion model to generate some high quality images from the Mayo Clinic dataset. We then train several denoising neural networks from the original dataset and synthetic dataset. Finally, we evaluate that the augmented dataset can improve the denoising performance. This is the architecture of latent diffusion model. We can use the latent diffusion model to create a synthetic data set. There are 3 images from the synthetic data set. We try to find the corresponding closest image from the original data set. We can see these 2 images look very similar, and however, some local structures are shown differences. To make a challenge, we assume a strong noise and treat several denoising neural network from original datasets and synthetic datasets. We can see this image left and right are from the original dataset and the synthetic dataset respectively. In this zoom view, zoom up view, up and bottom are from original dataset and the synthetic dataset respectively. From the results, we can see the results from different methods have some differences. However, for each method, the results are very similar. Same tendencies can be observed in this PSNR and SSIM, which illustrate that using the synthetic dataset to train the denoising neural network is a feasible approach. In information datasets, we have 2377 images. We augmented the dataset to 3000 and 4000 and then train the rate CNN in these different training images. We can see the PSNR is improved from 2377 to 3000, but limited by the scale of rate CNN from 3000 to 4000 just got a small improvement. The latent diffusion model also synthesizes some unrealistic data like these 2 images. However, we demonstrated that these kind of images have limited influence in denoising tasks. And also, I think we can solve this problem by optimizing the latent space features. Additionally, we can use the latent diffusion model to synthesize infinite data set to reduce resource cost and facilitate data sharing. Finally, the original dataset and the synthetic dataset keep the same distribution. Therefore, we can use the synthetic dataset to secure patient privacy. And then Dr. Chuang will present the next work.
Okay. Hello, everyone. I'm Chuang Niu. Actually, I'm the blue person. And yeah, next I will report our work on photon-counting CT super resolution. Photon-counting CT is promising technology for high resolution imaging. There are 2 types of detectors like CZT and deep silicon. Our lab is interested in deep silicon as early as in 2016. And generally, the high resolution, the better for imaging. And in this project, we aim to improve the resolution of PCCT images. The first thing is the key thing is to generate realistic low and high resolution PCCT images. So in this project, we use the advanced calcium PCCT simulator developed by Bruno's group. And the resolution was adjusted by modulating the detector pitch and the focal spot size. And the noises and the crosstalk were simulated in low resolution images. And in this project, we developed a 2.5D super resolution network because we found directly adapting the 2D diffusion model to 3D CT data is very challenging. Specifically, it is very challenging to get it converged. So in this project, we trained 2D networks using in-plane and through-plane slices. And then we develop efficient joint inverse diffusion process that alternatively does the inference to enforce the results from all 3 directions consistent. So this is the results on the inserted line pairs. Actually, importantly, these kind of structures were not seen in the training data. So we can see that the DDPM can obviously improve the resolution, especially for the high frequency structures, and it can outperform the baseline method, that is the conventional supervised learning method. And this is the result on the real structures, and we can see that DDPM can generate more detailed structures in contrast to the baseline method. And in summary, our proposed 2.5D super resolution diffusion model is both feasible and cost effective. And the DDPM can outperform the supervised baseline method. And also the model can generate well to the unseen line pair phantoms. We will continue work along this direction towards the clinical translation. That's all about this part. Thank you.
We'll only see you're trying to close this one down. So. Oh, okay, there we go. So, advance the slide. So this one won't advance, only this one. I don't know why it's not. Let's try restarting it. There you go.
Hello, everyone. My name is Wenjun Xi, and I will present our Sparse View CT reconstruction work using Denoising diffusion probabilistic model. And we know at present one of the most important methods for dealing the view CT data is two domain-based methods. But this method will introduce the information from projection data, making the results better. But this method will have to put the entire projection data into the memory, making it challenging for them to handle large-scale data. To overcome this issue, we propose the patch-based DDPM approach. In our method, the projection data is divided into patches, and DDPM model is applied in parallel to implement the missing information of these patches. And we evaluated the effectiveness of our approach using the simulated sparse view CT data from Mayo dataset. Here are some technical details. The DDPM model operates through a forward process that gradually adds noise to the patches from the normal CT data, and reverse process that recovers the patches from the noise. A neural network is then trained to learn the score matching function and help to realize the reverse process. During the reverse process, we interpolate the full data, CT data, and into the fully sampled shape to obtain the yield, and calculate its state at different time steps to obtain the yield t as the condition. This condition is used to interpolate with the intermediate reverse process results YT based on the downsampling mask M, so that we can recover the missing information through the reverse process. Our method achieved impressive results, closely matching the ground truth in terms of textures and details. The average PSNR and SCM value for the test set is shown in the table, indicates that our method yields high quantitative scores. As we continue to build on this line of work, we have identified three primary avenues for further research and development. Firstly, we will incorporate a deep domain network to further enhance image quality. Secondly, we aim to improve the sampling efficiency. And then lastly, we will extend our work to 3D DDPM, allowing us to process the 3D cone-beam CT data. Okay, my part is over. Next.
Okay, next I will introduce our work on large image model and large language model to build a multitask multi-modal learner. So over the time, the model size and the performance dramatically increased, even outperforming human. Especially the recent progress have shown that by unifying multitask and the interrelated data sets, the large language model and the large image model can be effectively trained, which can induce the informative embedding and emergent properties. Inspired by this progress, here we aim to optimizing a large hybrid model, including pre-training and downstream task fine-tuning to improve the performance of various clinical tasks. However, there are various challenges in building a medical large hybrid model. For example, for the 3D CT report generation, the first challenge is the high dimensionality. I think that is why most of current publications working on 2D medical report generation like chest X-ray images. The second challenge is the subtle and complex pathologies, and the third challenge is the sparse or imperfect labels. Maybe there is a very small region, like lung node region, is labeled in a relative high-dimensional 3D CT data. So it is very challenging to directly generate report given the high-dimensional 3D CT data. Actually, the radiology report generation involves many tasks like what kind of the nodule is, and where is the location, and what is the set, and so on. So in this project, we develop a multitask model with large image model and large language model. Currently, we mainly focus on semantic segmentation, object detection, and classification, which are the three main computer vision tasks. And we also interested in captioning. So as shown in this slide, this is our unified model. In our model, there are two inputs. One is the text, one is image, another is the text. And the visual encoder and text encoder will extract features of image and text respectively. And we also need a task token to tell the model which task will be conducted. The task token can be automatically learned and can also be generated by the text encoder. Here we design a new task attention block to extract the task-specific features. Then the task-specific decoders can predict the final results. Also, to process the high-dimensional 3D CT data, we use various techniques, like we use a long former, gradient checkpointing, model parallelism, and so on. And also, we pre-train the visual encoder using a relatively large 3D CT data set. So here are the results. So using only a single model, we can input a series, we input the 3D CT images, and then we input the text prompt, like segmentation of left lung. The model will output the left lung mask. When we input segmentation of right lung, the model will output a right lung mask. And we can also input the detection of lung nodule. The model will output the bounding box with the scores. We can also calculate the nodule size using this bounding box. And apart from inputting the 3D full resolution 3D images, we can also input a small ROI. Like then we can input like classification of different types of lung cancers. Then the model will output the corresponding scores. Actually, using all these results from these multitasks, we can easily generate a report using the current large language model, such as ChatGPT. But next, we will train our own model, the same model shown here, to generate a report. And we believe this unified model can be extended to many other modalities and tasks. So in summary, our pilot multitask results are promising, and the comprehensive comparison is in progress. Also, we will integrate more tasks and modalities and data to make our large model more powerful, and our implementation details will be shared very soon. Thank you.
Okay. Okay, so last slides, we should acknowledge grant support from NIH, NIBIB, and also industrial support, particularly General Electric. And we have been working together over decades. And also, I highly appreciate all NIH grant reviewers' effort. And you guys doing fantastic job. I would like to make important comment. A large model is a big thing. And last year, I did my sabbatical leave in Wake Forest radiology. So they have their radiology is Wake radiology is academic core of atrium healthcare system. So the system covers 6 states, so there are big data there. However, the data is in central part of United States. We are very open to collaborate with other medical schools, healthcare systems, so we can work together, make a really synergistic big model, open to discuss with you. So for questions, depending on color of your question, so we have RGB scheme. So if you have, for example, large model question, that's blue, Chuang will answer. So if your question is colorless, then I will answer. Okay.
Thank you.